Friends, we will continue the discussion on curved beams. This is lecture 33, curved beams 4, where we will continue to discuss the derivation of the geometric parameter small m and the eccentricity value E of the location of neutral axis from the centroidal axis for a curved beam with large initial curvature. Let us take an I section . Let us mark the plane OO which contains the center of curvature. Let the dimensions be B1, B2 and B3. We do not mark the thickness, but we mark different radius from the center of curvature or from the plane of center of curvature as R1, R2, R3 and of course, this is R4. We have the CG located here. Let us say that is located at a distance R from here. We can take a general strip which is Y from the centroidal axis. We are about to locate the neutral axis at an eccentricity E from the centroidal axis. We will also define this with a parameter V from here. Now, we know that M A is integral y plus r by y dA for the whole area, which can be y can be expressed as V minus r and r plus y is simply V integral dA, which can be dA minus r dA by V, which can be A minus r times of integral limits R1 to R2. The strip area is actually B1 into dV by V plus for the strip area of width B2, the limits are going to be R2 to R3 B2 dV by V plus again the last strip which varies from R3 to R4 B3 dV by V, which we can say this A minus R B1 log R2 by R1 natural logarithm plus B2 R3 by R2 plus B3 log R4 by R3. So, that is going to be my MA. Therefore, M is 1 minus R by A of B1 plus B2 plus B3 equation 1. E is then given by R minus A by B1 R2 by R1 plus B2 R3 by R2 plus B3 log R4 by R3. So, now we have got different sections, that is pure rectangular, a T section, an I section, which are actually sum of rectangles. So, one can now have a very general expression for sections which is sum of rectangles. E in that case will be R minus A by summation of 1 to n B n natural logarithm R n plus 1 by R n. So, that is the general expression we have for E. Once I know E, I can always find M. Let us go for a triangular section. Say this is B1, this is my OO plane and this is my CG, and therefore, this distance is R, and this is R1 and this is R2. As usual, we take a strip and let that strip be at a distance V, as a radius V from the plane OO. Let us say this distance is Y, and let us say the width of the strip be x. So, it is very interesting. Now, I want to estimate width of this elemental strip, that is x. One can use a similar triangle principle. You know, this value is actually equal to R2 minus R1, and this value is actually equal to B1 by 2. So, for R2 minus R1, we have a variation of B1 by 2. Therefore, this variation, which is R2 minus V, will be x by 2. So, with cross multiplication, x by 2 R2 minus R1 is B1 by 2 R2 minus V, which says x will be B1 R2 minus V by R2 minus R1. So, that is the width of the elemental strip x. Once I know this, MA integral dA minus R dA by V, which is A minus R integral. The limits are this, and the elemental area is the width of the strip into thickness is dy. This thickness is dy. So, B1 R2 minus V by R2 minus R1 into dV by V. So, MA is A minus RB1 by R2 minus R1 integral limits R2 R1 R2 minus V dV by V, which will be A minus RB1 by R2 minus R1 integral R2 dV by V minus integral simply dV, which will be A minus RB1 by R2 minus R1 of R2 by R1 log minus R2 by R1. Now, M straight away is 1 minus R by A R2 B1 by R2 minus R1 R2 by R1 minus B1, and E is R minus A by R2 B1 by R2 minus R1 R2 by R1 minus B1. So, now these are the two equations for estimating the location of neutral axis for a triangular section. Let us go for trapezoidal section. Look at the OO plane. Let us say this is B1, this is B2, and this is R1 and this is R2. Let us take a strip from the CG, which is at a radius r, which is located at a distance y, and let the width of the strip be x, and let the strip be located at a radius v from here. So, this is my centroidal axis. Of course, I will look at the neutral axis later here, which will be at a distance e from the centroidal axis. So, now to find width of the elemental strip x, let us say we know I can divide this as I am showing in the figure now. This width, which is B 1 minus B 2, will have a slope of R 2 minus R 1, because this distance is R 2 minus R 1. Therefore, the width will be x at a distance which is R 2 minus V. So, cross multiplying x 2 R 2 R 1 will be R 2 minus V B 1 minus B 2. So, x is B 1 minus B 2 R 2 minus V R 2 minus R 1, of course, plus B 2, because this is only the slope, is we are getting only this distance, which we can rather call as x star. Therefore, x will be actually equal to this plus B 2. Now, once I know this, I can now say my M A is integral d A minus R d A by V, which is A minus R integral limits R 2 R 1, which is B 2 plus B 1 minus B 2 by R 2 minus R 1 R 2 minus V of d V by V, which can be A minus R R 1 R 2 B 2 d V by V plus integral limits R 2 R 1 B 1 minus B 2 by R 2 minus R 1 R 2 d V by V minus R 1 R 2 B 1 minus B 2 by R 2 minus R 1 of d V, which now is A minus R B 2 log R 2 by R 1 plus B 1 minus B 2 by R 2 minus R 1 R 2 log R 2 by R 1 minus B 1 minus B 2, because when you get the limits and substitute, they will get cancelled, which will be A minus R B 2, because you know this term and this term can be combined, B 2 plus R 2 of B 1 minus B 2 by R 2 minus R 1 of ln R 2 by R 1 minus B 1 minus B 2. So, I can say M is actually equal to 1 minus R by A of the same parenthesis term, and E is R minus A by B 2 plus R 2 by R 2 minus R 1 of B 1 minus B 2 of R 2 by R 1 minus B 1 minus B 2. So, that is going to be my location of neutral axis towards the center of curvature measured from the centroidal axis. Interestingly, in the above equation, if we substitute B 2 equals 0, please see this figure. If B 2 is 0, it becomes a triangle. The expression will be used to calculate E for a triangular section. If we substitute B 1 equals B 2 equals simply B, we can get E for a rectangular section. So, it is very interesting. Above equation is used to locate the neutral axis from the centroidal axis. These equations are useful only to obtain the skin stresses on the extreme fibers in curved beams with large initial curvature. However, there are some simplified equations available to estimate the stresses. In the extreme fibers. This is given by Wilson and Curiel. They said stress is given by a factor K mh by I, where K is a factor to be used for intradas and extradas as below. For example, K intradas is m by mh, hi minus E by Ri divided by m hi by 2I. K extradas is given by H extradas plus E, you know the positive sign is being used accordingly, by R 0 divided by m H naught by 2I. So, this K I and K 0 are called correction factors. In fact, one can say stress correction factors. They are given by Wilson for different values of R by H. The factors are given. Both k I and k extradas are given. For both circular, where this is my plane of curvature and this is my R, and from the CG they are equidistant. If it is elliptical, still one can use the same equation, provided you know the dimensions and the depth of the section. For different values 1.2, 1.4, 1.6, 1.8, 2.0, 3.0, 4.0, 6.0, the factors k I and k naught are given. 3.41, 2.40, 1.96, 1.75, 1.62, 1.33, 1.23, 1.14, and these values 0.54, 0.6, 0.65, 68, 71, 79, 84, 89. For a rectangular section, where this becomes my plane of radius of curvature and this becomes my R and this becomes my depth of the section H, for 1.2, 1.4, for all ratios of R by H, the values are available as given in the table. Further, they have also given the tables extending it for E, where the beam is under pure bending. So, this is 0.224 R, 0.151, 0.108, 0.084, 009, 030, 016, 0070, this is 305, 204, 149, 112, 090, 041, 021, 0093. So, friends, we have seen how to estimate M and E for different shape of cross sections: circular, rectangular, series of rectangles, triangular and trapezoidal. We have also found approximate stress correction factors Ki and Ko to estimate stresses in the extreme fibers. We recollect that the Winkler-Bach equation is useful to estimate skin stresses only on the extreme fibers, because the stress variation along the section is hyperbolic, therefore, one cannot do that. So, one can find the maximum compression and tensile stresses in the extreme fibers using the Winkler-Bach equation. So, in the next lecture we will take up some numerical examples and solve them and find out stresses at various cross sectional shapes for a given moment for a curved beam with large initial curvature and so on. Thank you.